Swayam Prabha. Digital India. Educated India.
In my previous lectures, I have discussed about the low strain field test to determine the dynamic soil properties. We determine the velocity of the either shear wave or the P wave and the thickness of the different layer. I have discussed about the different conditions or the different layering conditions, horizontal layering, incline layering, different test methodologies, and then we, by using the available correlations, we can determine the shear modulus of the soil. Now today I will discuss about the large strain field test. Now first I will discuss about the standard penetration test, which is commonly known as SPT. So, the standard penetration test is widely used to determine the parameters of the soil in situ. The test consists of driving a split pun sampler into the soil through a borehole at a desired depth. So, that means to conduct this test we need a borehole, and within the borehole we drive a split pun sampler, okay, by applying hammer blow. Okay, that split pun sampler is driven into the soil at a distance of 450 millimeter at the bottom of the boring. So that means we have to do a borehole up to the desired depth. On that depth, we place the split pun sampler, and then we apply the hammer blow and drive that sampler tube. You can see here, this is the your split pun sampler, and up to that required depth, we drive it for 450 millimeter at the bottom of the borehole. And then once the test is done at that location, then we can go up to the further depth, and then we can do the test again, okay, with some interval. So the hammer of 63.5 kg weight with a free fall of 750 millimeter is used to drive the sampler. So this is the hammer whose weight is 63.5 kg, which is standard weight, and the free fall, height of free fall is 750 millimeter. Okay, so this is the chain pulley system by which we can conduct, in addition to the other methods are there by which also we can apply the hammer blow. The number of blow for penetration at least 30 millimeter is considered as the number n, SPT n value, or standard penetration value. So that means we will drive it for 450 millimeter. Now for 450 millimeter, we every 150 millimeter we count the number of blows required to penetrate that 150 millimeter. Okay, and then first 150 millimeter penetration value is neglected, and the last 300 penetration that value required number of blow to penetrate last 300 millimeter is considered as the n value. Now this test is usually performed in 3 stages. The blow continue to found every 150 millimeter penetration. The blows for first 150 millimeter penetration is ignored, and these required for the sitting drive. Okay, and then this is the animation. So that means we apply number of blows, and every 150 millimeter penetration we count the number of blows required to penetrate that 150 millimeter. First 150 millimeter penetration required blows to penetrate first 150 millimeter is called N1, then next N2, then N3, and then we add N2 and N3. That N2 and N3 will be the N value or SPT N. So, the number of blows for fast penetration due to the disturbance likely to exist at the bottom of the drill hole. Okay. The test can be conducted every 1 meter vertical interval, not more than 150 meter. So, that as I have mentioned. So, in interval we have to conduct the test, and when you will stop the test, okay, or the standard penetration resistance, when we say that this is the refusal of this test, stop means when if we reach up to my desired level, then we will stop there. Otherwise, if 50 blows are required for any 150 millimeter increment, then we have to stop the test. The 100 blows are obtained for required 300 millimeter penetration, or 10 successive blows produce no advance. If any of these three occurs in the field, then that will be the refusal of the test. Okay. So, then we have to stop the test, or up to the required depth we have to go. So, now when you get the N value, that is that N value we will use later on to determine that soil properties. So, now that I will discuss, there is all these large strain test, how we will get the soil properties from the large strain test, that I will discuss later on. Let me first discuss what are the different tests. Now, this once we do that, ultimately what I will get? I will get a N value, SPT N value, and as well as I can collect the samples from the, because that is a sampler. So, I can collect the sample, and that sample I can use later on in the lab to determine the soil properties. But here for this particular case of determination of dynamic soil properties, we will concentrate only the N value. So, we will get the N value, and that N value we will use. Okay. So, once we will get the N value, then that raw N value or the field measured N value, we have to apply different corrections. Okay. And why those corrections? I will discuss that. As per the IS code, IS 2131-1981, we have to apply two corrections. Okay. So, two correction, what are those corrections? So, that is first is overburden pressure correction, and next is dilatancy correction. So, overburden pressure correction is basically you have to normalize that N value with you can see that value is equal to, this correction value is equal to 1 when it is normalized with 10 ton per meter square or 100 kilonewton per meter square. So, we have to normalize that N value with respect to this 100 kilonewton per meter square, but vertical effective overburden pressure, Now, first we apply that correction. So, that correction, this is Cn. So, from the chart, so suppose we are doing at a depth of H. So, at that depth, what is the effective overburden pressure that we will calculate. Now, that overburden pressure, if it is 100, effective overburden pressure is 100 kilonewton per meter square, then no correction is required, because that Cn value will be 1. So, N value N dash will be equal to N. But if the effective overburden pressure is more than 100, then we have to reduce that N value. Okay. Basically, we are doing the normalization. So, we have to reduce that N value, because that if we go further below that or below the soil layer, then there will be overburden pressure will be huge. So, that means we will get the higher N value that we have to reduce. So, that correction, so that is why we will get if it is say greater than 100 kilonewton per meter square or 10 ton per meter square, then you can see for 20 ton per meter square the correction factor is 0.8. So, that you have to reduce it, but if it is less than 100 kPa or 100 kilonewton per meter square, then you have to increase the N value. Okay. So, you can see, so it can go up to 1.7. Okay. So, it can go up to around 1.7. After that, no. So, that is the maximum correction value, 1.7. Here you can see 1.2, actually it is 1.6. So you can see it is roughly 1.72. So that means here we have to reduce it if it is less than 10 ton per meter square. So once you do that correction, then you have to apply the dilatancy correction, and then dilatancy correction is that 15 plus 0.5 into n dash minus 15. That means this correction you have to apply if after overburden correction the n dash value is greater than 15. So that means first you will do the overburden correction, then if that n dash value is greater than 15, then you have to go for the dilatancy correction. Now why you have to go for the dilatancy correction? Because if the n dash value is greater than 15, the soil will be treated as a dense soil. So in that case there will be a dilatancy. Okay, that means if we apply the hammer blow, the soil will expand. There will be dilatancy effect. Okay, so if the soil will expand, then your negative pore pressure will generate, because you can see this dilatancy correction for saturated fine sand and silt. Okay, so that means saturated. So if it is expand, then the negative pore pressure will generate. So negative pore pressure will generate means your effective overburden pressure will increase, because your effective overburden pressure is total pressure minus pore water pressure, and if pore water pressure is negative, then it will be total pressure plus pore water pressure. So effective overburden pressure will increase. So your strength will also increase. So you will get higher N value. So that we have to reduce. So that's why by applying the dilatancy correction, actually we are reducing the N value. But now the question is that why we will not apply these things because these things when we apply the load in the real structure, then there may be dilatancy may be occur also. But the condition is in actual when we do that this SPT test, so this is under undrained condition. So that means under undrained condition means water will not get enough time to dissipate. So that means the pore water pressure will generate, but at the real foundation, below real foundation, the soil will be under drain condition. Okay, so that means here pore pressure will get enough time to dissipate. So that pore pressure, negative pore pressure will not generate. So that's why the strength will also not increase. So that's why in the real foundation this higher N value will not occur. Actually, so that's why we have to apply this correction to reduce that N value, which will give you the more number of more N value as expected. So, but this IS code is recommending that. But in addition to that, there are other corrections also there. So that is the standard blow count N-60 may be computed as per the ASTM D1586. So what this test says, that this says that we have to determine N-60. Okay, what is 60? N dash indicates it is your corrected, and Cn as the effective overburden pressure. Cn I will get from this expression. So this is also basically normalized by 100 kilonewton per meter square. This is 95.76, which is close to 100 kilonewton per meter square, that 100 kPa. Then this is the effective overburden pressure. Same as if your effective overburden pressure is equal to 100 kPa, then the Cn value is 1. Okay. So, and if it is less than that, then Cn value will be greater than 1. If it is more than that, then Cn value will be less than 1. Okay. So, you can use this Cn for effective overburden pressure correction. In addition to that, there are 4 corrections. What are those 4 corrections? That is the hammer efficiency correction, drill dot correction, sampler and borehole correction. So, I will discuss one by one. So, let me discuss what is the meaning of this N-60. What is the meaning of 60? 60 is the standard energy ratio value. The meaning is that suppose when we are doing the test, suppose we are doing n number of SPT test, and the applied energy, because we are applying an energy, because we are applying hammer blow. So that means the apply energy may not be same for all the test. But when you represent them, we cannot represent them because if your energy will be different, the different n value will be there. So we have to represent them in a single energy number, because suppose you in some tests are done under 80% energy, some is done under 60% energy, but we cannot represent them in different with respect to different energy. So you have to convert it to a single energy value, that is 60. That means 60 means this test is done under applying 60% energy. Okay. So sometimes it is also called N160. So these N160 will frequently use when I will discuss about the liquefaction of soil. So this N160 is very important. What is the meaning of 60? 60 is when 60% hammer energy is being applied. 1 means it is normalized with respect to 1 ton per feet square. Okay, which is same as 100 kPa. Okay, so that means 1 means it is, or you can say it is the same value as the atmospheric pressure. So it is normalized by 1 ton per feet square or 100 kilonewton per meter square. So that's why meaning of N160. 1 means normalized by this effective overburden pressure correction. So normalized by 1 ton per feet square and under 60% hammer efficiency. Now one by one I will discuss about what is hammer efficiency. That means hammer efficiency is ER by ERB. What is ER? ER means actual hammer energy that is applied to the sampler and is divided by input energy. So that means it is a standard test. So that means your standard height, standard weight. So now if there is a free fall, there will be energy that you are applying on the sampler tube. Okay, but in the field that actual value will be different to that value. But that means one is the theoretical value, another is the actual that energy that you are applying. If those are different, then that is your ER. And so you can see the ERB. ERB is this is ER is the ERB means at what energy value we want to represent the N value. So ER is representing that. ERB is standard energy ratio value. So that means I want to represent it, say 60% hammer efficiency, but in the field you have applied 80%. So that applied 80% means ER, and ERB is that at which energy value I want to represent the N value. Okay, so you can see if you use different hammer, or then ER value will be different. So that is given here for rope pulley or cat head, that is 45 ER value, 45, and for US, for Japan it is 67, for China it is 50. For trip or automatic hammer, that is for 78 for Japan and 60 for China. Rope pulley and cat head it is mentioned. The safety hammer with that is for these hammer blows, or for safety hammer it is rope pulley or cat head, it is your 70 to 80 in US and 50 in UK, and trip or automatic hammer for 80 to 100 in US and 60 to UK. Now if your ER is 80, so that means you are say at applying trip or automatic hammer, that value is 80, and standard energy ratio value is 60. That means you want to represent it at 60% hammer energy, but your ER value is 80. Okay, that means you have applied 80. So that means the N value that you will get with applying the 80. Now, if you convert it to 60, then your n value should be increased. So, that is the case. So, 80 divided by 60, so that will be 1.33. Now, if it reverse, then you have done it in 60, but now you want to represent it in 80. So, that means n value will reduce. So, then in that case, it will be 60 divided by 80. So, generally the standard one is N160. Okay. So, that is the meaning of this 60 and 1. Now, in addition to there are corrections for rod length. So, if you see that n value is too high if the rod length is less than 10 meter. So, that means for 10 meter it is 1, if less than that it is too high. So, you have to reduce it. So, that you can see for 6 to 10 meter is 0.95, 4 to 6 meter is 0.85, 0 to 4 meter is 0.75. Similarly, for sampler, now it is saying n is too high if it is with liner. The sampler has a liner, it is too high. So, that means if with liner, then you have to reduce that. So, without liner it will be 1. So, without liner it is 1. And if it is with liner for dense sand and clay, it is 0.8, you have to reduce, and loose sand it is 0.9. Now, if it is other way, you can see that if with liner n value is too high, without liner n value will be too small. So, that means you have to increase that. So, that means standard sampler with liner in that case will be 1, and without liner it will be 1.1 and 1.3. Okay, so there any one you can use. Now, correction factor for borehole diameter, n value is too small when there is an oversized borehole. So, that means if the oversized borehole n value will be too small, so we have to increase that. So, if it is borehole diameter is standard 60 to 120 millimeter, this correction is 1. But if it is 150, correction is 1.05, it is 200, correction is 1.15. So, we have to apply all the corrections. So, now for the actual case, if when we use this N160 for liquefaction, then we should use this method to apply all these corrections, and you apply the energy correction also, apply the borehole correction, drill dot correction, and then sampler correction. So, all these corrections you apply, and then that one you use for this liquefaction problem that I will discuss. Clear? So, that means because those charts are developed with respect to N160. So, energy correction you have to apply. In addition to that, these all corrections you have to apply. Remember that. So, now I will go to the example problem. Say n value, given value is 21, rod length is 13 millimeter, borehole diameter is 100 millimeter, effective overburden pressure is 20 kPa, ER is 80, loose sand without liner, what will be the standard for N-60 or N-70 and 60, or N160 or N170. So, this is for 70, these are the corrections. So, Cn it is 100 by 200 around within root, so it is 0.69, and N1 will be 80 ER, and ERB here is 70, so it will be 80 by 70. N2 means it is the correction, this means it is your rod length correction. Rod length is 13 meter, so it is for 10 meter 30 greater than 10 meter, so it will be 1. Okay, rod length will be 1, then your hole diameter is 100, then means that will be also 1. 100 means that will be also 1. Now, it is loose sand without liner. If I use this one, that loose sand without liner or with liner, what? Loose sand without liner. So, that will be also 1. So, these all are 1. So, then you apply that, you will get the measured 121, now it is 17. So, we are applying all these corrections, and then we are getting 17. Now, the same way you can do it, just change it. Now, just you can make 80 by 60, and then you can do, or other way you can do this way also, you will get the N160. So, which is same as doing 80 by 60. Okay. So, you will get the same for N160 also. So, this way you can get the value of N160 or N-60. So, now next one is the cone penetration test. So, cone penetration test will be two types: dynamic cone penetration test DCPT and the static cone penetration test SCPT. Here we will discuss mostly the SCPT value. Now, dynamic cone penetration test is similar to SPT where you apply the hammer, but for static cone penetration test, here the cone will be pushed into the ground at a rate of 1 centimeter per second. Now, using cone instead of split pun sampler, but in DCPT we use cone, not the split pun sampler, but it is done at an interval of 1.5 meter. But in SCPT, the reading is given continuously. Okay. Now, the SPT, these are the SCPT description as per the IS 4968 1967. 76, you can get all this value that it is, there are different parts, with 4 parts. This consists of steel cone, this is steel cone, then friction jacket, then sounding rod and the mental tube. So, I will show in detail. So, these are 4 parts in this equipment. The cone has a apex angle of 60 degree plus minus 15 minute. The overall base diameter is 35.7 millimeter, having a cross section area of 10 centimeter square. The friction sleeve should have an area of 150 centimeter square. Now, sounding rod, a steel rod which is diameter is 15 millimeter and can extended with additional rods of 1 millimeter each in length. So, we can attach 1 millimeter additional rod and then we can go up to the required depth. Similar to SPT also, we can apply the add the additional rod and we will go to the up to required depth. So, diving mechanism should have a capacity of 20 to 30 kilonewton for manually operated equipment and 100 kilonewton for mechanically operated equipment. Now, let me explain that this is the one particular position that SCPT test. So, these are the sounding rod, then this is the mental tube, yellow one, then the friction jacket is the black one and cone assembly is this blue one. So, first stage, this is the first stage. In second stage, what we will do? We will push the, you can see the push the only cone assembly by 40 millimeter. So, when you push the cone assembly 40 millimeter, you will get the resistance. So, we will note down that resistance, that will give me the cone resistance or the tip resistance QC. Okay. Now, in the next stage, this is the next stage. Next stage, we will push the cone assembly as well as the friction jacket assembly all together. So, here I will get the total resistance cone plus friction. Now, if I subtract the cone resistance from the total resistance, I will get the friction resistance. Clear? So, that in first stage I will get the cone resistance, second stage I will get the total resistance. Now, if I subtract the cone resistance from the total resistance, I will get the friction resistance. Next stage, the mental tube is pushed by 40 millimeter. In the final stage, again the mental tube and the friction jacket assembly will be pushed by 40 millimeter to bring it in its original position, so that we can take the next reading. Clear? Okay. So, now these are the different depth versus SPT and the cone resistance QC value for a particular soil. Now, the friction ratio means, as I know how I will get the cone resistance I have discussed, or the tip resistance, and the sleeve friction or the friction resistance Fs. Now, if friction ratio Fr is basically Fs divided by Qc, and based on the cone resistance and friction ratio, I can classify the soil also, okay, by using this chart. The next test is the dilatometer test. So, here dilatometer test, so it is also pushed into the soil. So now remember that the SPT we need borehole, but SCPT we don't need borehole. Even the dilatometer test also we don't need borehole. So here this is my dilatometer, which is a flexible steel membrane, and then we will push it, then we will apply the pressure to expand it. Okay. So this is advanced at a rate of 20 millimeter per second. Test every 20 to 30 millimeter interval. The nitrogen tank is used for inflating the membrane. So that means we have to inflate the membrane and then we will get the resistance. And so that inflating the membrane, we use the nitrogen tank is used, and it gives the several soil properties, and it can identify the soil also. And then we can use it for our determination of seismic soil properties also. So that is the your test setup. Now that means it is also pushed inside the soil, and then at a different interval we inflate that membrane and you get the data. Now what data we will get? From there, first we will get the horizontal stress index, that is called KD. So KD is what? KD is P0 minus U0 divided by sigma V0 bar. Sigma V0 is the effective overburden pressure and U0 is the pore water pressure. Okay. And P0 is the contact stress, that is the pressure required to just begin to move the membrane. That means the pressure that is required to just begin the movement of the membrane. So that means how much pressure we have to apply just to begin the movement of the membrane, that is called P0. And there is another term is P1, that is the expansion stress, that is the pressure required to move the center of the membrane by 1.1 millimeter into the soil. So that means the P0 is the just the stage where it is begun to move the membrane, and P1 where how much stress, expansion stress, this is called expansion stress, that means how much stress is required to move that membrane, center of the membrane by 1.1 millimeter within the soil. Okay. So or into the soil. So that means the center membrane, it will move, that is pushed into the soil. So within the soil it will move. So that is called P1. So from there I will get KD and ED also. What is ED? It is called dilatometer modulus. So later on I will use this ED and KD to determine the dynamic soil properties. I will show that, I will explain. Now KD is kilonewton per meter square, it is 34.7. Remember that, this is important, this unit only you have to use because it is 34.7. It is the empirical expression. So P1 minus P0. Clear? And another term which is called material index, ID, that also we can get by using this expression. Based on ID we can classify the soil. Now, if your ID is in between 0.1 to 0.6, it is classified as clay. If it is 0.6 to 1.8, then silt. If it is 1.8 to 10, it is sand. Clear? So, we can classify the soil by using ID, and this KD and ED will use to determine the soil properties. So, next or the last test, that is the pressure meter test. Here also the pressure meter consists of that inflatable cylindrical probe which is connected into water reservoir. Here also it will inflate, and that cylindrical probe is connected to water reservoir. The expand cylindrical probe inside a borehole. That means here we need a borehole. Within the borehole we place that equipment, and then we expand that cylindrical probe within the soil laterally. Because vertically we are providing to support, these are called guard cell. What is the function of guard cell? It will not expand that cylindrical probe in vertically. Okay, it will allow the expansion of the cylindrical probe in the lateral direction only. Okay, now the probe press against the wall borehole so that soil began to deform. The volumetric deformation of borehole is measured by noting the fall of water level into the water reservoir. So, by measuring the fall of water level, we can measure how much volumetric expansion is there into the cylindrical probe. So, this is described in this IS code. So, now what are the things we will measure? So, first we should know what is the V0, that means the volume of the probe which is inserted into the borehole. So, that is V0, capital V0 is the volume of the probe. So, this measuring cell or the probe, volume of the probe, that is capital V0. Now, that means here we will apply the pressure and the volume change will be measured. So, that means we apply pressure and corresponding volume change we will measure and we will plot it. So, x axis is the volume and y axis is the pressure, and you will get this type of curve. So, if you look at this curve, there is three parts. This is the zone 1, this is zone 2, this is zone 3. So, you can see the pressure is applied in increment and volumetric expansion of the cell is measured. Now, we have three zones. First zone 1 it is called reloading zone. So, reloading zone means, that means here, so when you do a borehole, so that means the soil will, this pressure will be released within the soil due to this borehole, then soil will, some portion will, soil will come to the center of the, towards the center of the borehole. Now, when you apply this pressure through the probe, then the soil will again go to its original position. So, that is called reloading zone. So, that means actually this portion where the P0 and is the portion where soil will go to its original position. After then it will start deforming again. So, that means that is called reloading zone, and then we can identify P0 and PF. How we can identify? If you look at this curve, you will find this in the middle portion it is almost straight. You can see the middle portion it is almost straight. So, we identify these 2 points. The initial one is called, the straight portion is called P0, and this final of this straight portion is called PF. So, the zone above the P0 is called reloading. Within the P0 to PF, it is called pseudo elastic zone, because you can see it is a straight line. After that, it is called plastic zone, and PL represent the limit pressure. How I will get the limit pressure? PL I can get by the capacity of this instrument, how much it can apply the pressure, so by capacity, or if the volume expansion is 2 times capital V0 plus small v0, then that is called PL. Now, what is capital V0 I have discussed? Small v0 means the volumetric expansion corresponding to the P0 stress, that is called V0. So, that means that is V0 plus small v0, and corresponding to PF it is VF, and this one is the VM is the average, that means P0 plus PF divided by 2. So, that means you can see Vm is the V0 plus Vf divided by 2, del P is the Pf minus P0, del V is the Vf minus V0, mu is the Poisson ratio, and V capital V0 is the measuring say volume, that is standard generally 535 centimeter cube, and Ps is the limit pressure that I have discussed. So, from there I will get the pressure meter modulus. So, that pressure meter modulus will be used to determine the dynamic soil properties. Okay, so this pressure meter will be used by using these, will be calculated by using these expressions. Clear? So, now if I summarize all these 4 tests, so you can see the SPT and the PMT they need boreholes, but the SCPT and DMT they don't need boreholes. So, these are the 4 tests that I have discussed. Okay. So, in the next class I will discuss that what are the different types of laboratory tests. So, I have already discussed the low strain field test and the high strain or the large strain field test. Now, in the next class I will discuss about the same as low strain laboratory test and the large strain laboratory test. Thank you.